On to a new situation. We see a cart with no friction connected to a horizontal spring. The cart oscillates between endpoints x equals negative a, negative amplitude, remember, and positive a, positive amplitude, where a is the amplitude of oscillation, and x equals 0 at the center and the equilibrium of the oscillation. We see that during the oscillation, the energy is in the form of spring potential energy and the endpoints of oscillation. The energy is kinetic energy at equilibrium. At all other points, the energy is a mixture of kinetic and spring potential energy. If we consider only the system consisting of the cart, let's get me out of the way here, then the mechanical energy is only the kinetic energy. We know this by now, Mr. Scapettes. We don't consider the spring's potential energy because the spring is not included in the system. The weight and the normal force on the cart are perpendicular, so they are not doing any work. The spring's force is external to the cart system and does work. When the spring force does positive work, the cart's kinetic energy increases. And when the spring force does negative work, the cart's kinetic energy decreases. Watch carefully. When does the spring force do positive work and kinetic energy increase? Where is kinetic energy at its maximum? Equilibrium. Spring force and the cart's motion are in the same direction. This occurs when the cart is going towards x equals 0, towards that equilibrium spot right here. So whenever the force is directed towards 0, there's positive work happening. This occurs because the spring is returning to its natural length as the cart goes towards x equals 0. So the cart does positive work to change its spring potential energy into kinetic energy. The spring force, therefore, does negative work when the cart is moving away from x and the spring is being stretched or compressed away from its natural length, which is when the spring force is acting in the opposite direction of the cart's motion. If we consider the spring cart system, then both the kinetic energy of the cart and spring potential energy are included in the mechanical energy. So now we have kinetic energy and spring potential energy in this system because we are including the spring. Now there's no external forces doing work. Weight and normal are external, but they're performing no work because they're perpendicular to displacement. And normal means perpendicular. That means there's no way for the mechanical energy to change, so the total mechanical energy is constant. If we add friction to the situation, the story is going to change some, of course. By now, I'm hoping you can already predict what's going to happen to the total mechanical energy. We should be decreasing because friction is doing negative work to slow it down. This is a dampened oscillation situation, remember? There's an external force acting on it, so it's slowing it down. As the block slides, friction is removing mechanical energy and dissipating it. The strength of friction force is constant, but the friction force does more work when the block goes faster, because work equals force times displacement. And if there's a greater displacement, and because there's a greater displacement when the block goes faster. Now, if we consider only the block as the system with the friction now, the only energy is going to be kinetic energy. Increases when the spring force is in the same direction as the block's motion, and the spring force is stronger than the frictional force. Your kinetic energy is going to decrease when friction is stronger than the spring force, or both forces are opposed to the block's motion. Looking at the block spring system, including both kinetic and spring potential energy and the mechanical energy, this energy can only decrease because the only external force that's doing work is friction. Friction only does negative work because friction is always directed opposite of the block's displacement.